We are Capstone Group 51 working on the FPGA-based automated 3D mapping of mines using UAVs. With the guidance of our esteemed mentors Dr. Manu Bansal and Dr. Anil Singh, we aim to design a flight controller on FPGA using hardware descriptive language for automated UAVs, contributing to the advancement of mine mapping technology. Now moving on to the introduction of team members. Hello, I am Saloni Garg, student of Electronics and Communication Engineering.
I am Muskan, student of Electronics and Computer Engineering.
Hello, my name is Yuvraj Verma and I am a student of Electronics and Computer Engineering.
Hello, my name is Sharma and I am a student of Electronics and Computer Engineering.
My name is Pulkit Garg and I am a student of Electronics and Computer Engineering.
For the hardware of FPGA-based UAV, we have used brushless DC motors with 1400 kilowatt ratings, electronic speed controllers to derive the motor with current consumption of 30 amperes. Propellers along with motor are used to generate the thrust for our quadcopter to lift it from the ground. The receiver of 2.4 GHz is used to receive the PWM transmitted values from RC transmitter. 6-axis motion tracking device MPU6050 sensor is used in our project, but we have used its 3-axis gyroscope to get the current position of our drone. FPGA basis 3 board is used in a project which takes the input from MPU 6050 sensor and the receiver and gives the calculated output in the form of PWM signals to ESCs, which derive the motors according to the duty cycles. To power the setup, we have used 2200 milliampere batteries. To design the flight controller, we have integrated various modules which are explained further in the video.
First module is PWM decoder module. This module is responsible for decoding the input signal from the RC receiver. Transmitter outputs 6 PWM channels at 50 Hz. The signal from the transmitter are being received by the RC receiver, and each channel of this RC receiver would have PWM signals as its output. So the width of this PWM signal actually depicts the movement that the drone will portray. So as it is shown in this diagram, that it is having the high level duration from 1 milliseconds to 2 milliseconds. 1 milliseconds depicts approximately 0 throttle, whereas 2 milliseconds corresponds to 100% throttle. And in this module, the width of this PWM signal is being measured and it is sent to the other module. This is the simulated waveform of PWM.
We have is the I2C communication, and in this we have two modules, I2C master and MPU driver. I2C master is a generic inter-integrated circuit communication master used to read and write the data to and from the MPU 6050 sensor. It controls two communication lines SDA and SCL to get the data from the sensor. To control I2C master, we use MPU driver. MPU driver provides the command to I2C master. It controls the state of the I2C master using the command signal. It also sends the acquired data from the gyroscope sensor to main control unit for drone controlling PID algorithm. Here we have 16-bit output from each of the axes of gyroscope sensor, 8-bit of which are MSB and 8-bit is displayed on the 7-segment display of the FPGA board. To control each of the X, Y, and Z axes, we can do it from the bottom right two switches. Right now for 0, 0, it is for X axis, for 0, 1, it is for Y axis, and for 1, 0, it is for Z axis.
Now let's move on to the PID controller. For the control of UAV parameters such as altitude and velocity, the PID controllers continuously compares the input process value to the set value and calculates the input error signal. This error is then used to generate the control signal through a combination of three intermediate signals named proportional, integral, and derivative terms, which can be given as these equations. The proportional gain determines the immediate response to any error, whereas integral gain eliminates the steady state error by accumulating past errors, and the derivative gain anticipates future error based on the rate of change to achieve the excellent stability and performance. Properly tuned discrete PID controllers are used for our UAV. They require less memory and processing power compared to the continuous implementations. These are the simulation results for our Verilog design for PID.
Now, in the PWM encoder, the main objective of this module is to encode the output signal received from the FPGA in a PWM format. The signal is sent to the electronic speed controller as it uses a PWM protocol for communication. Electronic speed controller, as its name suggests, is used to control the speed of the motor by interpreting the signal received from the flight controller and control the speed of each motor by varying its duty cycle of the signal. The PWM signal generated should have a width of 1 to 2 milliseconds, where a width of 2 milliseconds shows 100% throttle and a 1 millisecond shows throttle of approximately 0%. Here we have a behavioral simulation of the PWM encoder.
So next comes battery monitoring system. This basically helps us to continuously monitor the battery percentage left in our UAV without the help of any type of external device. We have our circuit diagram on the left. So our circuit diagram is basically consisting of LM3914 IC, resistors, potentiometer and LEDs. And the other picture that is on the right side shows us the live dot display of a circuit. It basically corresponds to the battery level in 10% increments. Next, the circuit is basically designed to monitor 10 volt to 15 volt DC supply, but the circuit will work even if the battery voltage is 3 volt. Also, there is no type of requirement of any resistor in series with LED because all of the current is regulated by our IC. LM3914 IC is basically the heart of our system because it supports different type of functions, like it supports wide range of temperature, and also no type of multiplexing interaction is required between the outputs. Thank you.
Next is camera module. We are using OV7670, which is 0.3 megapixel camera with 614 to 480 resolution. So this is a flow diagram of the process. Camera interface module, it retrieves the pixel data from the camera device and passes it to asynchronous sweeper module. Static dynamic RAM interface module, it controls the logic sequence for storing the pixel data that is received from camera interface module and passes further it to asynchronous sweeper module. And VGA interface module, it passes the pixel data that is received from static dynamic interface module to the VGA core module. This is the simulation waveform for the same.